Hey everyone and welcome. Have you ever looked at a tiny little microcontroller and just wondered how on earth can its single processor core do so many things at once? I mean, it really does feel like magic. Well, today we're going to pull back the curtain on this incredible one-core illusion. Let's get right into it. So, this is the big mystery we're going to solve. You see it all the time. It looks like multiple programs are running completely on their own, all at the exact same moment. But here's the thing. On a single core system, what's really going on is so much more clever than that.
Here's the secret. They aren't running at the same time. Not really. It's more like a high-speed juggling act, and the juggler is a special piece of software called a task scheduler. This scheduler is basically the heart and soul of what's called a real-time operating system, or an RTO for short. So let's properly meet this task scheduler. You can think of it like the conductor of an orchestra, or maybe an air traffic controller for your CPU. It has one job and one job only, to decide which task gets to use the processor at any given millisecond, making sure the whole show runs smoothly. Okay, so how does it know when to make these decisions? Well, it listens for something called a system tick. This is just a regular, repeating signal from a hardware timer. It's like a metronome for the processor, usually ticking every single millisecond. And at every single one of those ticks, the scheduler wakes up and asks, all right, who's up next? And this timeline here shows you that basic rhythm perfectly. See, at tick 1, the scheduler runs and says, okay, task A, you're up. For the next millisecond, task A gets to use the CPU. Then, at tick 3, whoops, the scheduler interrupts again, takes a look around, and maybe lets task A continue. This is called time slicing, and it happens so incredibly fast that to us, it looks like everything's running at once. But of course, the scheduler doesn't just pick tasks randomly. No way. It follows a very strict rulebook. And the 3 most important ideas you need to get are task priority, the different states a task can be in, and this really powerful concept called preemption. This right here is the golden rule. It is so simple, but it is incredibly powerful. Let's say you have 10 tasks, and they're all ready and waiting to go. The scheduler is just going to ignore 9 of them and immediately run the one with the highest priority. That's it. Simple as that. Now, a task's life isn't just on or off. It's actually moving between several different states. A task is running when it's, actually using the CPU. It's in the ready state when it could run, but it's just waiting its turn because a more important task is running. It becomes blocked when it's waiting for something to happen, like for a timer to go off. And finally, it can be suspended, which is like being put into a deep sleep until another task comes along and wakes it up. And this brings us to the coolest part, in my opinion, preemption. This is what makes a system feel so snappy and responsive. It's the scheduler's power to just forcibly interrupt a running task if a more important, higher priority task suddenly needs the CPU right now. Let's paint a picture here. Imagine you have a low priority task, we'll call it task A, and it's just chugging along doing some long, boring calculation. Suddenly, something happens. Maybe a button is pressed. That makes high priority task B ready to run. What do you think the scheduler does next? Exactly this. The moment that next system tick happens, the scheduler looks around and sees that the more important task B is ready. It doesn't politely wait for task A to finish up. Nope. It immediately yanks the CPU away from task A, it preempts it, and gives full control over to task B. Now, theory is great and all, but let's actually see this happen. We're going to check out a really simple Arduino example that makes this idea of preemption something you can literally see with your own 2 eyes. All right, so our first task has a low priority. Its entire job in life is to print a long, silly pirate sentence to the screen. But here's the key. It prints just 1 character at a time. And this little bit of code shows you why that's so important. By printing 1 character at a time inside this loop, we're creating these tiny little gaps, these little pauses between each letter where the scheduler can interrupt. If we just told it to print the whole sentence at once, it would be over before we could even blink. Okay, our second task is way simpler, but it has a higher priority. All this one does is wake up every 100 milliseconds, print a single asterisk, and then go right back to sleep. And this code is its whole world. It prints the star, and then it calls vTaskDelay. That function is what puts the task into that blocked state we talked about. It's basically telling the scheduler, hey, I'm done for now. Wake me up in about 100 milliseconds, okay? And here it is, the grand finale. This is the actual output from the code. Do you see it?
Every single time you see one of those asterisks, that's our high-priority task waking up, rudely interrupting, preempting the sentence printing task, doing its job, and then going back to sleep, which lets the pirate sentence pick up where it left off. That is preemption made visible. Pretty cool, right? So there is one final piece to this whole magical puzzle that we need to talk about. How can the scheduler just stop one task and start another without the whole system just crashing and burning? I mean, how does task A remember where it left off? Well, the answer is a process called context switching. A context switch is basically the process of freezing everything about the current task in time. It saves what line of code it was on, all the values in its variables, the state of the CPU registers, all of it. It saves that entire snapshot, and then it loads the saved snapshot of the next task that's about to run. And it all happens in this lightning-fast 3-step dance. So as you see, step 1, save the complete context of the task that's running. All its data gets saved to its own private memory area. Step 2, load the saved context of the next task from its memory. And finally, step 3, the new task just resumes running like nothing ever happened, exactly where it was paused. It's this seamless swap that makes the whole illusion of multitasking possible. So now that you know the secrets of the scheduler, here's a little challenge for you to put it all into practice. Can you write a program with 2 tasks? One task that just blinks an LED over and over, and a second totally separate task that listens for input from your computer to change that blink rate. This is a classic RTOS problem, and now you've totally got the tools to solve it. Good luck!